14.7. All right, so a reminder, in chapter 11 we had an introduction to cylindrical coordinates. So I just want to remind everyone what our cylindrical coordinates are. We can think of cylindrical coordinates as polar coordinates plus a z. So we have x equals r cosine theta, just like in polar coordinates, y equals r sine theta, and z equals z. And what we're going to do is I'm going to draw a little portion of the xy plane, or the polar plane. The other day, this is our theta equals 0 and theta equals pi over 2 axis. We came up with a way to find the area of a little, what we called a polar rectangle. So we said, if that was our little polar rectangle, make that solid, that this, we could think of this side as delta r sub I, and this arc is the average radius at that particular point times delta theta sub I. And so in polar coordinates, we said our delta A sub I was r bar sub I, delta r sub I, delta theta sub I. So we're going to use this. Basically what we're doing is taking this little piece and we're projecting it, kind of drawing it up into 3 dimensions. So if I draw my 3-dimensional axes here, and we're going to make a 3-dimensional, not a rectangle, but kind of a polar prism. And since we're in 3 dimensions, we would call it a cylindrical prism, I guess. So a little chunk of a cylinder. There's my y, and there's my x. So in the xy plane, we still have this. So that's going to be our projection in the xy plane. And we're going to think of the same angle up here in space, but now we're going to have a little piece, a little chunk of a cylinder. Let me draw this first. I'll do that. So that's going to be our side, but this edge and the front edge are curved. And so this side, this little side of our little chunk of the cylinder is going to be the delta r sub I. This piece is r bar sub I delta theta sub I. And the height here is delta z sub I. So our volume then of that little piece is going to be delta v sub I is going to be r bar sub I. I'm going to say delta z sub I, delta r sub I, delta theta sub I. That's going to be a little representative piece of volume in cylindrical coordinates. So we're just adding that z coordinate. So we're going to, if we have some function that's defined over this region in space, we can multiply this delta v sub I times our function. It could be a mass per unit volume. We've done several different things. We're going to form the sum, add them all together, take the limit as delta v sub I approaches 0. So I'm not going to go through all that, writing all that out, but we'll say form the sum over the region, and we're going to take the limit as delta v sub I approaches 0. And again, when we take that limit, what we're saying is the longest diagonal of the little chunks that we've divided the region into goes to 0. And that's going to be our definition of, so we're going to sum over all those pieces in that region, and that will give us our definition. This corresponds to our definition of a triple integral. But now we're going to use these coordinates instead of rectangular coordinates. So we get that the triple integral over our region Q of f of x, y, z dv is going to be, and we can evaluate this as an iterated integral, and I'm going to write it in the usual order from theta 1 to theta 2, from g1 of theta to g2 of theta, the integral from h1 of r theta to h2 of r theta. And then we express our function, whatever the function is, in terms of cylindrical coordinates. So that would be r cosine theta, r sine theta, z, r dz, dr, d theta. So theta varies from theta 1 to theta 2. R varies from g1 of theta to g2 of theta, so we could have r as a function of theta. And z is some function of r and theta to some other function of r and theta. And we always have this r in here. So the outer double integral corresponds to our double integral in the plane in polar coordinates. So once we evaluate that first integral, the z integral, we have the double integral r d r d theta, which is our integral in polar coordinates in the plane. This is our most common order of integration, r dz dr d theta. Just like with rectangular coordinates, you can set up your integrals in any permutation of dz dr d theta. But this is going to be the vast majority of integrals you set up in cylindrical coordinates are going to be in this order. And we use cylindrical coordinates for when we have our region. When our region in the xy plane is easy to represent in polar coordinates. It's nice. And we can also think when we have circular symmetry about the z-axis. Now, when we talk about spherical coordinates, often it's easy to represent this kind of region in spherical coordinates also, so you have a choice. But some regions in spherical coordinates are very easy, where in cylindrical coordinates they're just easy. All right, so questions about our setup? Okay, I just have 2 examples today. The second example, we're going to set up a particular triple integral in cylindrical coordinates, and then tomorrow we'll do the same integral in spherical coordinates. Kind of do a compare and contrast. This is that example, the second example today, and the one we'll do in spherical is my favorite example, I think, of multiple integration. This one's pretty good too, though. I was thinking while you were taking the quiz, I was thinking how it's kind of, the weather's kind of changing, it's turning to spring. Don't multiple integrals make you think of flowers coming up and blooming?
Right.
Yeah, doesn't this look like a flower? Yeah, and they're nice. Yeah.
start sneezing and coughing whenever we get here, though.
What are you trying to do?
Yes.
That's my makeover street.
That's not nice.
All right, we want to convert to cylindrical. All right, so the limits always tell us about our region, and I think when you can kind of visualize the region, it's going to be easier to set up. So from the limits, we have x squared plus y squared is less than or equal to z less than or equal to 4. So what is that? So what is z equals x squared plus y squared? Paraboloid. What is z equals 4?
Plane.
A plane. So what is this region describing? We're inside the paraboloid, right? This is a little sketch. There's our paraboloid. So there's our region, and here we're at z equals 4. So we're inside this parabola. Z goes from the paraboloid to the plane z equals 4. So we can visualize z going from here to here. Well, this region minus 4 square root of 4 minus x squared less than or equal to y less than or equal to square root of 4 minus x squared. That's a circle. So this y equals square root of 4 minus x squared, that would be a cylinder. But in the xy plane, what we're doing is we're projecting this down into the xy plane. And there's that circle, x squared plus y squared equals 4. So this is telling us our region in the xy plane, and x is going from -2 to 2. So in the xy plane, if I drew a sketch in the xy plane, we have this circle. And x is -2 to 2, and this y is going from negative square root of 4 minus x squared to positive 4 minus x squared. So that's our region in the xy plane. All right. Well, this is pretty easy to convert to cylindrical coordinates, right? So we have theta is going to go from, in this region, 0 to 2 pi. We can't necessarily split it up because we have this x in there, so that's not symmetrical in that region. R is going to go from 0 to 2. There we go. And z is going to go from r squared to 4. And then we have x.
R squared cosine theta.
So we'd have r cosine theta, r d theta. I'm just leaving that. Oh, so I forgot my z. R dz d theta. All right.
All right, now let's solve it though.
Well, let's r dz. Well, let's use our encyclopedic knowledge of applications of triple integrals to evaluate this without doing any calculus.
What? Stop.
What does the triple integral of x dv give us? Well, we're multiplying x times the volume. X is the distance from what?
The y-axis.
The yz plane. What's the triple integral of the distance from the yz plane times a little piece of volume? If we think of our density as 1.
The moment.
Isn't that the moment about the yz plane? Well, how is this? What's going on with this in relation to the yz plane? Here's the YZ plane.
It's on it. It cuts through it.
It cuts through it.
They're symmetrical.
Symmetrical.
So zero.
The moment about the YZ plane is 0.
Equals 0. It's that easy, Kevin.
That's it. I can see how that goes.
It's not an area, Dylan.
This represents M some YZ.
Dylan.
The moment about the YZ plane, it's symmetrical about the YZ plane. There's the same amount of mass on this side of the YZ plane as on the other side of the YZ plane, so the moment is 0. Isn't that nice?
I'd never be able to do that on a test.
What's that?
I'd never be able to do that on
If you recognize that on a test correctly, and you said this represents M sub YZ and the moment is 0, you'd be set.
What if we just guess 0 on every one? We got to try something.
Well, you'd have to tell me why.
Because I guess.
Oh,
Just bullshit.
Connor, by the way, natural log of E is 1.
Yeah, you know.
I had a student 2 years ago that that wrote that on the test, and I took a half a point off on a quiz, and then on the next test, every time there was a 1, she wrote natural log of E. So it was like 20 times on the test, just to spite me. What's that? Are we period natural log of E? All right, questions here. This is a pretty nice example. This next one is better.
So dumb.
So we want to find the volume of the solid inside the sphere x squared plus y squared plus z squared equals 4. I won't take a half a point off from yours, Connor. I'll be nice this time.
Don't give my D's.
Take natural log of E points off.
Oh.
Yeah.
Ooh. So 0?
All right, we want to find the volume of the solid. Excuse me. Inside the sphere, x squared plus y squared plus z squared equals 4, and the upper portion of z squared equals x squared plus y squared. So let's draw a picture, because this represents something really nice. Here's our sphere. X squared plus y squared plus z squared equals 4. Here is our cone. I know it's not beautiful and perfect. There's where the cone intersects the sphere in the first octant. So what we want is the volume that's underneath this sphere inside the cone. We want the volume of the ice cream cone. Because if I cut all this other stuff away, I'd have something that looks like this. We're trying to find that volume. So we're finding the volume of the ice cream cone. So it was the first year I taught this class, I remember telling the class, I really love triple integrals. And one of the students from Broomfield, she says, Mr. Beamer, I love ice cream. So the next day, we were doing this, and I said, well, here we go, triple integrals and ice cream all together. All right, so z is going to vary from the cone to the sphere. So that's going to be our limits of integration on z. Well, we need the region in the xy plane that defines this. So we need to project this down to get our region in the xy plane. Well, how are we going to find that region? When what's equal? We want to find where the cone and the sphere intersect, right? And then we're going to project that down into the xy plane. The cone and the sphere intersect where I can set these two, or z squared is x squared plus y squared. So I get, I'm going to substitute this in for x squared plus y squared. 2z squared equals 4. And that means z equals 2. Square root of 2, right? And we just need the positive one because we're talking about the upper portion of the cone. And if z equals the square root of 2, x squared plus y squared equals 2. So this circle in the xy plane is x squared plus y squared equals 2. That's going to be our region in the xy plane. Well, this is a nice integral to set up now in cylindrical coordinates. So I'm going to say our volume equals the integral. Theta goes from 0 to 2 pi. I could split it up, but this is not going to be a bad one to evaluate. Radius goes from 0 to square root of 2. And z goes from the cone to the sphere. Z goes from z equals the square root of x squared plus y squared, so z equals r. There we go. And it goes up to the sphere. Z equals 4 minus x squared minus y squared. Square root. So square root of 4 minus r squared. In cylindrical coordinates, the equation of this sphere is z equals 4 minus r squared. And then we have r, dz, dr, d theta. Easy integral to evaluate. After our first integral, I'll do the first one. V, we get the integral from 0 to 2 pi, the integral from 0 to square root of 2 of rz, evaluated from r to square root of 4 minus r squared. Z is evaluated there, times r dr d theta. Nope, dr d theta. R is here. So we end up with, for our integral in polar coordinates, in the plane, 0 to 2 pi, 0 to square root of 2, of r square root of 4 minus r squared, nice easy u sub, minus r squared, dr d theta. What does the theta integral do? It just multiplies, gives us a multiple of 2 pi. So we just have this nice r integral to evaluate. When we evaluate that, we get 8 pi over 3 times 2 minus square root of 2. So the volume of the ice cream in that ice cream cone is 8 pi over 3, 2 minus square root of 2.
So that's how cubic feet
Right. So next time you go to get some ice cream, you can ask them to make sure they give you this quantity of ice cream. Right. Cubic.
Well, that includes the cone.
Yeah, well, I guess we're assuming the cone is infinitely thin, right?
Yeah.
Actually, make sure we just
All right.
How long do you have?
All right, question.
Application.
And the other student from Broomfield in that other class worked at an ice cream shop.
Wow.
So yeah, what a coincidence.
Yeah, where do you wish?
And then that's the class where the girl from Broomfield, the student from Broomfield, and one of the students from Monarch both went to Purdue, and they ended up being roommates.
Wow, what a small
Yeah.
world. Imagine being
All right.
Wow, thought of being
Wow.
He said we're doing 2 examples, dude.
Wow.
Chilling.
There you go.